In this problem, we have a description of this subspace of R3. W is contained within, or I guess, R4. So W is a subspace of R4, and U is some other vector that's not a member of W, but is a member of R4. And ultimately, our goal is to find the projection onto subspace W of vector U. So to do that, what do we need to find first? How do we typically, or what's our general method for projecting any vector onto a subspace?
You find the, go ahead.
Mm-hmm.
You find the projection matrix. Is that what it's called?
If we can find a projection matrix, usually written as capital P sub W, or whatever the name of the subspace is, the idea is that's a matrix you can multiply by any vector you want to create the projection of that vector onto that subspace. So whatever, I mean, geometrically, if we have some subspace W, which in this case is 3-dimensional rather than 2-dimensional, but I'll just draw it as a plane for now. And U is some vector that's not a member of that subspace. We're going to create a new vector that is as close to U as possible and is a member of that subspace. And that matrix should be, or that vector can be written as the projection matrix times U. We just need to find the projection matrix first. Any questions on the goal of that so far, what we're trying to accomplish here? So how do we find the, sorry, go ahead. Was there a question on that? Okay. So how do we find this projection matrix? What's our usual procedure for creating the projection matrix based on having a basis for the subspace?
We turn the vectors into a matrix.
Do we have a procedure or a formula for building that?
It's A times A transpose A, the inverse of that times A transpose.
Sorry, what was that? Or have you seen a formula for this? Yeah, the A times A transpose A inverse times A transpose. And what does A represent in this case? Or how would we build the A matrix? Or what could we use as matrix A here?
The spin. Oh, go ahead.
Yeah.
Yeah, if we take these three vectors,
Yeah.
the three vectors that are, or however many vectors are a basis for the space we're talking about, we want to use those three vectors or however many vectors as columns for a matrix. So if we just take those vectors and treat them as columns, we can think of W as the column space of this matrix. So this is really the projection matrix for projecting not just onto any subspace, but specifically for projecting onto the column space of A. So we have a general formula for projecting onto the column space of any matrix. But you can use that for any subspace, because if you have a basis for it, you can just use the basis as columns for a matrix, and then the column space of that matrix is the subspace we're talking about. So we can just take this A matrix and run this calculation on it, and that will create the projection matrix. We can then multiply that projection matrix by any 4x1 vector we want, such as this one, to find the projection of that vector onto this subspace. Any questions on that procedure so far? Then let's run the calculation. A transpose A, we're going to, and I would do this first because that's in parentheses. So find A transpose A, invert it, left multiplied by A, right multiplied by A transpose. So A transpose, we just need to flip this over, treat every row as a column and every column as a row. So A transpose would look like each row is now a column, and each column is now a row. And now we just need to multiply A transpose times A. And by the way, what would the dimensions of that be? If A transpose is 3 by 4 and A is 4 by 3, what would be the dimensions of the result?
4 by 4?
4 by 4, not in this case, because we've got A transpose, which is 3 by 4, times A, which
Oh,
is 4 by 3.
It'll be 3 by 3. Yeah.
Right. If we swap the order, if we had A times A transpose, then that would be 4 by 4.
Oh, yeah. Sure.
But generally, the inner dimensions matching up, the fact that these are the same dimension tells us this can be done. And then the outer dimensions tell us the dimensions of the result. And those don't have to be the same, but they will be if we're talking about transpose of the same thing. So the result is going to be 3 by 3. And we can just multiply, combining a row of A transpose with a column of A. So if we combine that row and column, for instance, first row, first column, 1 plus 1 plus 1 plus 0. First row, second column, we have 0 plus 1 plus 1 plus 0. That's 2. First row, third column, 0 plus 1 plus 1 plus 0. So that's also 2. And then we combine the second row of A transpose in every column of A. So second row, first column, 0 plus 1 plus 1 plus 0. Second row, second column, 0 plus 1 plus 1 plus 0. And second row, third column, 0 plus 1 plus 1 plus 0. And likewise, the third row of A transpose in every column of A. So third row, first column, 0 plus 1 plus 1 plus 0. Second column, 0, 1, 1, 0. And third row, third column, 0 plus 1 plus 1 plus 1. So that is A transpose A. Any questions on that calculation so far? And then what do we need to do with that?
We multiply it with A transpose.
Not
No, find the
yet,
inverse
we
of it.
need to First, yeah, we need to invert that. And then multiply the inverse on the left side by A and on the right side by A transpose.
Mhm.
And how would we find the inverse of this matrix?
You take the find the determinant and then 1 by the determinant into the adjacent matrix. Is that right?
How would you form that then?
Sort of like keep the diagonals the same and you swap the not exactly sure.
The shortcut there where you just swap the ones on the diagonal and take the opposites to the other ones, that only works if it's a 2 by 2. It's a very useful shortcut if it's a 2 by 2. Like if you have A, B, C, D inverse, you take 1 over the determinant and then swap the ones on the main diagonal and take the negative of the other ones. This does work for a 2 by 2, and it's a very useful shortcut anytime you're dealing with the 2 by 2 inverse. But it only works for 2 by 2. This one is not. Yeah, if you augment this matrix with the identity matrix and then row reduce, that should work. That's the more general procedure. So let's try that out. If we have 3, 2, 2, 2, 2, 2, 2, 2, 3, augmented with the identity matrix, then we'll want to row reduce to make the left side into the identity matrix, which should be possible unless this isn't invertible. As long as this is invertible, we should be able to turn the left side into the identity matrix, and whatever remains on the right side will be the inverse of the original matrix. So how could we do that? What would be some row operations that would work here? Do you see any ways to turn the left side into the identity matrix?
Well, I noticed that everything on the second row is 2, so I divided by 2.
Yeah, one way would be to divide this by 2, which would also lead to a 0, 1/2, 0. So it might be better to wait on that, because not everything in this entire row is all multiples of 2. You certainly could multiply that by 1/2, but I think it might be better to do that in a later step.
Can
In fact,
you
in
do,
general, sorry, go ahead.
oh, no, go ahead. Yeah.
Oh, I was just saying that we do ultimately want every pivot to be a 1, but that's usually easy to do as the very last step. Like if you have a pivot that's a 5, you can just divide that row by 5 at the end. So I usually wouldn't worry too much about making the pivots into 1s until the very end. If you do notice an entire row is all multiples of some number, then I would go ahead and divide that out immediately just to simplify the numbers. But in this case, dividing the second row by 2 would lead to this 1 turning into a 1/2, which might make the numbers more tedious to deal with. So I think in this case, I wouldn't divide that by 2 yet. You certainly could. There are many ways to get to row reduced echelon form, but I think it would be easier if we don't do that just yet. Multiply row 1 by 2/3 and add it to the second row. Yeah, that would be the default next step, or the default first step, because we'd want to use the first pivot to eliminate the numbers below it. However, even though that's the default first step in the standardized Gauss-Jordan elimination process, I think in this case, there might be a slightly easier way to do it other than the standardized method. The standardized method is really useful because it takes all the decision-making out of it, but sometimes there may be some shortcuts that make the calculations easier if you diverge a little bit from that method. Do you see any other ways that you might combine these rows in unusual ways to make the numbers much easier to work with? Is there any way you could rapidly get a row of the identity matrix right away?
Can you like for row 1, you subtract row 1 by row 2?
Yeah, because if you take row 1 and subtract row 2, what's left in row 1?
1, 0, 0.
Right. And that's just a complete coincidence here. That won't be necessarily true for any other matrix. But it's a good idea to keep watch for shortcuts that might happen to show up in certain specific matrices. That if you don't really see any obvious way to proceed, the Gauss-Jordan method, the standardized step-by-step, use this pivot to eliminate everything below it, that's always there. You can always use that if you don't see anything else to do. But it's not always the most efficient way to do it. It's not always the fastest, easiest way to get the calculations done. So also be on the lookout for shortcuts that might save some time and effort and make the calculations easier as well. And let's try that in this case. Let's subtract row 2 from row 1. In that case, we'd have 3 minus 2, 2 minus 2, 2 minus 2. So just by the way the numbers happen to be arranged, that's going to make it a lot easier to work with. And then continuing, 1 minus 0, 0 minus 1, 0 minus 0. And the second row we'll leave as it is for the moment. But do you see anything else you could do similarly with the third row that would make that easier to work with?
The same thing, but for like subtract row 2 from row 3.
Yeah, if we take row 3 and subtract row 2, then that, again, just by coincidence of how these numbers happen to work out, is going to make things a lot easier. 2 minus 2, 2 minus 2, 3 minus 2, then 0 minus 0, 0 minus 1, 1 minus 0. So I would recommend be on the lookout for specifically situations where one row is a duplicate of another row or a multiple of another row, or looks almost like another row except for one small change. Even if it diverges away from the standardized procedure, sometimes you can do a quick operation ahead of time to make things much easier. Because now we can use the standard Gauss-Jordan elimination in just a couple of steps. If we start here and proceed, what would be the next step in the standardized procedure? For instance, if we think of it in terms of the pivot in the first row, and we want to use that pivot to eliminate everything under it, yeah, if we just multiply row 1 by -2 and add it to row 2, so we're modifying row 2 by adding -2 times row 1. And also, while we're at it, our final row has a pivot here. How could we use that to eliminate this too?
Just the same thing, but just from row.
Yeah. Let's try both of those in one step. And of course, you can
Okay.
always split it up into 2 steps as well. I'm just thinking that since we've got a 1, 0, 0 here and a 0, 0, 1 here, we can probably combine these into one step without too much extra trouble. So we'll have first row not changing. Third row not changing. In fact, the first and third rows are done. We don't need to make any further modifications to the first and third rows because those already look like the identity matrix or the corresponding rows to the identity matrix. The middle row, though, we're taking the middle row and adding -2 times the entire first row and adding -2 times the entire third row. So 2 minus 2 minus 0 is now 0. 2 minus 0 is still 2. 2 minus 0 minus 2 is 0. So by doing both of these operations combined, we were able to cancel out both of these 2's. And then 0 minus 2 minus 0 is now -2. 1 plus 2 plus 2, because we're adding -2 times this number and -2 times this number. So 1 plus 2 is going to be 5. And 0 minus 2 times 0 minus 2 times 1. So that's just 0 plus 0 minus 2, -2. Any questions on that step so far? And at this point, this is now almost in reduced row echelon form. What's the only thing we still need to do?
Divide by 2, the middle row, the second
Right,
row.
divide that entire second row by 2. So it looks like what's left, that is A transpose A inverse, is just this matrix, the right side, because we now turned the entire left side into the identity matrix exactly. Whatever remains on the right side is the inverse of the original. So 1, -1, 0. And then we're dividing the second row by 2. So -1, 5 halves, -1. -1, 5 halves, or 2.5, whatever you want to write it as. And then -1 again. And then 0, -1, 1. So we now have A transpose A inverse. Any questions on that so far? So now that we've got A transpose A inverse, what do we do with that?
Multiply it with like A transpose on the right.
Yeah, A transpose on the right and also A on the left. So we'll just combine all those together and let's see what that's going to look like. So we've got matrix A exactly as it is. Multiplied by this inverse we just found. I'm going to go ahead and write this as 5 halves. I think that might be easier to work with. And then A transpose. So that's this one. So we multiply these together, and you can choose any adjacent pair to start with. The first one times the second one, and then that times the third one. Or multiply the second one times the third one, and then the first one times that result. You just need to keep the left to right order consistent. So if we multiply all those together, that should give us the projection matrix. So let's say we multiply the first one times the second one. And that is a 4×3 times a 3×3. So we should expect the result to be 4 by 3, which means I'll probably want to draw this a little larger. And this is just going to be combining rows and columns as usual. So 1 plus nothing plus nothing, -1 plus nothing plus nothing, nothing plus nothing plus nothing. And then 1, 1, 1 combined with each column. So 1 plus -1 plus nothing is 0. -1 plus 5/2 plus -1. In other words, 2.5 minus 2. So that's 1/2. And then nothing plus -1 plus +1. So that's 0. And then third row, 1, 1, 1. That's going to be the same. We've got the same row combined with the same columns. So we'll get the exact same results. And then 0, 0, 1. In fact, you could kind of think of this as a transformation matrix. What would 0, 0, 1 do with these rows? What information should we be getting if we're just multiplying by the rows 0, 0, 1?
Only the third row?
Yeah, just the third row, because we'd be taking 0 times everything in the first row, plus 0 times everything in the second row, plus 1 times everything in the third row. So we'll just have the third row exactly as it is. In the same way that, for instance, 1, 0, 0 meant keep the first row exactly as it is. So it's often useful to think of matrix multiplication as transform matrices, especially if you're multiplying by a matrix that has lots of ones and zeros anyway. So that's the first times the second. We would then multiply that by the third matrix. And this, since we've got a 4 by 3 times a 3 by 4, this should result in a 4 by 4 final result. So again, combining rows and columns, 1 plus nothing plus nothing, 1 plus -1 plus nothing, same thing, 1 plus -1 plus nothing, and 0 plus 0 plus 0. And then second row in each column, nothing plus nothing plus nothing, 0 plus 1/2 plus 0, 0 plus 1/2 plus 0, 0 plus 0 plus 0. And then the third row is exactly the same. So same third row combined with all the same columns is going to give you exactly the same result anyway. Then final row combined with each column, we're going to have nothing plus nothing plus nothing, nothing plus -1 plus +1, still 0. And the same nothing plus -1 plus +1, still 0. 0 plus 0 plus 1. So this, at long last, is our projection matrix. P sub W, in the sense that it projects anything onto W. So we should be able to now multiply this matrix times any vector we want. And the result will be a new vector in a subspace W that's as close as possible to that vector. Any questions on that so far? So this matrix times this vector, switch to a different color. PW times U is this matrix.
I got a quick question.
Yeah, go ahead.
So the PW should always be on the left, right?
Yes.
And then okay.
Yeah, in general, if we're talking about a matrix that's being used as a transformation on some column vector, it's the matrix on the left times the vector on the right. If you reverse the order, if you have a vector times a matrix, that only works if the vector is a row vector instead of a column vector. So if you're talking about row vectors, you'd be putting the vector on the left. But usually we describe vectors as columns, so we put it on the right.
Mm-hmm. Gotcha. Okay.
And you could generally think of something like this as treat the matrix as a function that takes a vector as input and gives you a vector as output. This vector is the input, the output, the final result we get is going to be the projection. So you could think of the projection matrix as a function or an operation that's applied to a vector. Taking some vector as input and giving you a new vector that's guaranteed to be in the vector space as output. So we'd multiply this out. Again, column or row by column as usual. -3 plus a whole bunch of nothing. 0 plus half of 4 plus half of negative 4, another 0 plus half of 4 plus half of negative 4 plus nothing, and then nothing plus nothing plus nothing plus 1 times 3. So this will be the projection of vector u onto this vector space. Any other questions on that one? Or any other questions about projection matrices in general?
Can you show me like what this would look like graphically?
This one we can't really draw in full because we're talking about
Oh.
4-dimensional vectors.
Oh yeah, true.
But you could think of it as, if we ignore the fact that this isn't actually going to look like the reality, because the reality is more dimensions than our own universe has. You could think of this as W is some sort of nebulous 3-dimensional space. And U, so W is a 3-dimensional space in a 4-dimensional universe. Much like, for instance, a plane, like a wall or something, is a 2-dimensional subspace of our own 3-dimensional universe. In this case, W is a 3-dimensional subspace of a 4-dimensional universe. And U is some vector that's not part of that subspace. So vector subspace W has 3 dimensions, let's say length, width, and breadth. And U has one more dimension that makes it beyond a 3-dimensional subspace. But we are taking the shadow of that vector onto space W. So this would be the projection matrix, projection vector, projection of U onto W. So if you think of it as like there's a bright light shining perpendicular to the subspace, then the projection is the shadow that that bright light casts of the vector. Any other questions on that?
So in this case, the -3003, it would be like the dotted one, or would it? No, it would be the.
That would be the one flat in
Yeah.
space W.
Okay, got it.
Yeah, so this vector that's not in W is -3, 4, -4, 3. And the flattened shadow in W has coordinates -3, 0, 0, 3. Any other questions on that one?
No.
All right, then let's continue to the next part, which is asking to find an orthogonal basis for W. That is, we already have a basis for W, but are these vectors orthogonal to each other? Or how would we check?
We can get the dot product and see if it's equal to 0.
Yeah, so if we take, for instance, the dot product of these two vectors, what do you get?
The angle.
That's-
Yeah, 1 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 0. So that's not going to be 0, right? And I think we can say the same thing about like this one dot this one or this one dot this one. None of these pairs are perpendicular to each other because none of the dot products end up being 0. So that means if we want a new basis that is orthogonal, then we'll have to orthogonalize it using the GramSchmidt process. So for the GramSchmidt process, let me label these. Let's call these, let's say U1, U2, and U3. And our goal here is to create 3 new vectors. Let's call them V1, V2, and V3 that still have the same information. They're still enough to span the same subspace W. But we want the new vectors to be guaranteed to be orthogonal to each other. We want a set of new vectors V1, V2, and V3 that still span space W. That is, we still want them to contain all the same information. We want to be able to build all of the same vectors with linear combinations. but we want them to all be orthogonal. That is, any pair of them, like V1 and V2, V1 and V3, and V2 and V3, we want all those dot products to be 0. In other words, we want them to be orthogonal to each other, perpendicular. Any questions on that so far? So to construct these, we use this idea of the GramSchmidt process. Which is, we're going to be building these new vectors one at a time, taking information from the original vectors U1, U2, and U3. But each time we take some information, we're going to remove some parts if necessary, so that whatever is left is perpendicular to everything we have so far. For the first one, V1, we're just going to take usually U1. You can actually take any of these vectors you want. The order doesn't really matter. You can get different results, different perpendicular perpendicular bases, but any space has infinitely many different bases anyway. So there are multiple possible answers here. Let's just take the first vector, U1, and do we need to make any changes to that? No, we can just keep that exactly as is. Because the idea is we want to modify each one to be perpendicular to everything we have so far. But if we haven't chosen any vectors yet, we don't have anything so far. So there's no reason to modify this. We can't really say this is not perpendicular to what we have so far because we don't have anything yet anyway. So the first vector, whichever one we choose to call the first one, we can just leave exactly as is. So let me write that in. We got 1, 1, 1, 0. Then the second one, we're going to take another vector, let's say just U2. But the problem is that is not orthogonal to the one we're now calling V1. So what do we do to make it orthogonal? What do we have to do to turn this into an orthogonal vector?
To do projections.
Yeah, this is ultimately all about projections. If we have this vector, the original vector U, specifically U2, and we also have this vector V1. Hello, we're working on using projections to orthogonalize a vector space with the GramSchmidt process. So we've got these three vectors that are a basis for some subspace W in R4, and we're making a new basis that is guaranteed orthogonal. So we're assuming that V1 is just the same as U1 because we don't need to change the first one. For the second one, the idea is U2 is not already orthogonal to V1. So we're going to split it into components. You could think of this, not necessarily the usual XY components, but a component in the V1 direction and a component perpendicular to that. In fact, you could even think of those components as vectors in their own right, because they do have direction associated with them. We've got a vector in the same direction as V1, or possibly the exact opposite direction, but parallel to it anyway. And another component perpendicular to that. We might even call those U2 perpendicular and U2 parallel, in the sense of parallel to V1 and perpendicular to V1. And we can think of this as vector addition. If you follow the parallel component, and then from there follow the perpendicular component, you get the whole vector. So we can say by vector addition, the parallel component plus the perpendicular component equals the original vector. But we can also write those in some other terms. Of these, which is the component we actually want to keep?
U2.
Well, U2 is what we started with, but which component of U2 do we actually want?
U2 parallel.
The parallel component is just in the same direction as what we already have, though. We want a new direction.
So U2 perpendicular, but wouldn't that just only be perpendicular to V1? Oh wait, that's what we need. Oh yeah.
But the thing is, V1 is the only part we've established so far. And
Uh,
this is really the advantage of building it one step at a time. We establish some direction. We create a new direction that's perpendicular to the one we have so far. And then in the third step, we're going to create a third new direction that's perpendicular to both of those. And then if there was a fourth one, we'd create a fourth vector that's perpendicular to all three we have so far. But the advantage of building it one step at a time is you only have to worry about being perpendicular to what you have so far. And then the rest will follow later on. So we just need to create a vector that's in a direction perpendicular to the V1 direction we've already established. This is essentially like creating a coordinate system. We've created an axis that we're calling the V1 axis. We're going to create another axis that we call the V2 axis, and then a third axis we could call the V3 axis. But the important thing about establishing a coordinate system is you want all the axes to be perpendicular to each other. It wouldn't be very useful, for instance, to have like XY axes like these. You certainly could set up a coordinate system like that, but it would make all the calculations we really care about much more difficult. It's much more convenient to have a coordinate system where the axes are perpendicular to each other. No matter what direction they're in, they've got to be perpendicular to make the calculations worthwhile. So we're going to ignore the parallel component. We want to focus on just the perpendicular component. And algebraically, how would you solve this for just the perpendicular component?
Subtract U2 parallel to the other side.
Exactly. If we just subtract the parallel component from both sides, we find that U2 perpendicular is U2 minus its own parallel component. That's really the key to the whole GramSchmidt process. We're taking U2, which is in a direction that's not quite convenient. We're subtracting the part that we don't want, the parallel part. By subtracting the parallel part, all that's left is perpendicular. So we're taking the whole vector, deducting the part that is not necessary, the parallel part that just duplicates the V1 information. All that's left is going to be perpendicular to V1. And in terms of notation, the perpendicular component is the V2 we want. So V2 is U2 perpendicular component. So V2 equals U2 minus, and then what would we call the parallel component? What do we call it when you take a vector and flatten it onto a direction of another vector?
Projection.
Yeah, this is where this ties into the idea of projections. That U2 parallel is just the projection of U2 onto the V1 direction. So to find V2, we take U2 and subtract the projection of itself onto the direction we already established. So this is what I was saying about getting rid of everything that's in the same direction we've already created, so that whatever's left is a genuinely new direction that's perpendicular to the other. So this is the core of the GramSchmidt process. We take the vector from the original set, we subtract this projection onto the direction we've already created, and whatever's left is guaranteed to be orthogonal. And then of course you can check the result by taking a dot product. You should end up with 0. Any questions on the geometric theory behind that so far? So to actually calculate that projection, in this case, we don't need to go through all of the trouble of setting up a projection matrix, because we're not projecting U2 onto a plane or a 3-dimensional subspace or something. We're just projecting U2 onto a 1-dimensional subspace, projecting onto a single vector or the direction of a single vector. So what formula could we use for that? If we want the projection of U2 onto the V1 direction, what's the usual dot product formula to find that very quickly?
Like B times A divided by B, well, B dot A over B dot B times and then another dot B.
Well, in this case, what are B and A?
B and A are
What are the vectors we're actually dealing with here?
U's.
U2, and also the direction is going to be the V1 direction.
Okay.
And I find it's easy to get lost in all the A's and B's or U's and B's or whatever the name of the variables are. So I usually think of this in terms of more like names rather than variables. If you're taking the projection of some input vector onto a direction, because we can think of U2 as an input vector that we're applying some operation to, and V1 can be thought of as the direction we're trying to create, or the direction we're projecting onto. You could write this as a fraction times, specifically a fraction times the direction vector, because we want to create a new vector in the same direction as the target direction vector. We accomplish that by just taking a scalar times that direction vector. And that scalar is made up of dot products, specifically input dot direction over direction dot itself. So this is really the main idea of the dot product formula for projections. You've got a scalar times the direction vector you want. And that scalar, or that fraction, is input dot direction over direction dot itself. The idea being that input dot direction describes how the input vector and the direction vector interact geometrically. But that gives us too much influence from the direction vector, so we divide by its magnitude squared, direction dot itself, to cancel out the extra influence. In this case, what's the input vector we're using here?
U2.
Yeah, so we take vector U2. And what's the direction vector we want to cast it in?
V1.
Yeah, so we'll use V1 everywhere we see direction. And as a quick check, the idea is we want to create a vector that's in the same direction as V1. This is a scalar times V1, so it will be in the V1 direction. So we can use that as a replacement for projection of V1 onto U2. Any questions on that so far before we start running the actual calculations? So we can rewrite the projection using this formula. U2 minus U2 dot V1 over V1 dot itself times V1. And to run that calculation, let's try actually filling in the numbers and see what we get. That should give us the perpendicular component by taking the original vector minus the parallel component. All that's left should be perpendicular. So filling in the actual numbers, we've got U2 is 0, 1, 1, 0 minus a fraction times V1, and V1 was the same as U1, so that's just 1, 1, 1, 0. And to find that fraction, we'll take these dot products. What's U2 dot V1 going to be if you take that dot product?
2.
Yeah, because we've got 0 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 0. What about U1 dot itself?
Would it be 3?
Yeah, 1 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 0. So that means the projection is 2/3 times 1, 1, 1, 0. In other words, 2/3, 2/3, 2/3, 0. But that's the parallel component. To find the perpendicular component, we take the original U2 vector minus that projection. The original vector minus the parallel component. So we've got 0 minus 2/3 of 1. 1 minus 2/3 of 1. 1 minus 2/3 of 1. And 0 minus 0. So that's V2. We get negative 2/3, 1/3, 1/3, 0. as V2. And that should be guaranteed perpendicular to the original V1 vector, which we could check using dot product. Any questions on that calculation so far? And one other thing I would recommend doing here, this isn't strictly speaking part of the GramSchmidt process, but it's an extra step that's going to make the next calculations much easier. All we really care about for V1 and V2 and V3 is their direction. We don't really care what size they are. If we do care about what size they are, we're going to be normalizing them later anyway. Eventually, we might want to make these all into length 1. But right now, we don't care about their size. We just care about their direction. V1 is in some direction. V2 is perpendicular to that. And V3 is going to be perpendicular to both of them. But if we change the size, that doesn't modify whether they're perpendicular or not. And what could you do to a vector that will change its size but not change its direction?
Divided by a scalar?
Yeah, divide or multiply by a scalar.
Yeah.
Is there any scalar that you might want to multiply this by to make the numbers easier to work with?
1 by 3?
Yeah, if we multiply this whole thing by 3, then the numbers are going to be much easier to work with. And we can do that because it's not going to change the direction. The vector will still be perpendicular to the original V1. It'll just be 3 times longer. But that doesn't matter because all we care about is direction. Again, not strictly necessary, but I would recommend doing this just to make the next calculations easier, because we're going to need to use this vector in our calculations for V3. And it's going to be a lot easier to work with if it's whole numbers. U2 was the original vector from the original basis for W. So U2 was split up into a parallel component and a perpendicular component. We take the original U2 vector and subtract the parallel component. So whatever's left is just the perpendicular component. And that perpendicular component is what we're calling V2. So let's multiply that out. We just multiply by 3, that clears all the denominators, and we get just -2, 1, 1, 0. So that's what we're going to call V2. So we've got V1 and V2, and our next step is going to be to build V3. Any questions on the vectors V1 and V2 so far? So let's build V3. Keeping just the information we're going to need. For V3, as you might expect, we're going to start with U3. But the problem is, comparing it to everything we've built so far, U3 is not perpendicular to V1, and U3 is also not perpendicular to V2. We need to modify it so that it's perpendicular to both of them. And we can do this one step at a time. First of all, what would we have to subtract to make sure that what's left is perpendicular to V1?
The projection of U3 on V1?
Yeah, if we subtract the projection of U3 onto the V1 direction, that's the component of U3 that's parallel to U1, or parallel to V1. Remove that by subtracting it, and whatever is left is guaranteed to be perpendicular to V1. But it's not perpendicular to V2 yet, so what else do we also need to subtract?
Projection V2.
Yeah, the projection of that same U3 vector onto the V2 direction. That way we're taking a vector that is in somewhat in the same direction as V1 and somewhat in the same direction as V2, and also somewhat in a third direction. We're removing the part that's in the same direction as V1 and removing the part that's in the same direction as V2. Whatever is left has to be perpendicular to V1 and V2. And that's our entire goal here. So we can fill in both of those projections with the usual formula, the dot product formula. For this one, we want a projection that's in the direction of V1, so it'll be some fraction times V1. And then the other one, we want a projection that's in the direction of V2, so we'll have some fraction times V2. And then the fractions are going to be the same format of input dot direction over direction dot itself. So input U3 dot direction v1 over direction dot itself. And then same thing here, input dot direction, which in this case is v2 over direction dot itself. So v2 dot v2. So this calculation should tell us v3, the third vector that is genuinely a third different perpendicular direction. Any questions on that setup so far? So let's run the numbers and see what we get. U3 is 0, 1, 1, 1. As for
Just
the projections, sorry, go ahead.
quick question. Quick question. Yeah.
Mhm.
So what if you look at so why can't the V1 sort of cancel out? Like
These ones,
yeah.
they kind of do, but remember this dot product is not the same as multiplication. If it was like times of scalar and divided by that same scalar, they would cancel out. But dot product is not quite the same thing as multiplication. It behaves in a lot of similar ways, but it's not quite the same thing.
Okay, that makes sense. Okay, gotcha.
One way you could write it that does kind of cancel out. Have you seen the cosine formula for dot products?
Yeah, no, I remember it. I don't properly remember. I remember
I think this has a lot more to do with how dot products are usually used in other branches of science, usually physics. If you have a vector dot another vector, with the components, we calculate them by multiplying the components and adding the results together. But that also happens to be equal to magnitude of one of the vectors times magnitude of the other vector times cosine of the angle between them. So if you actually write out u dot v over v dot itself, you'd have, I'm not going to bother writing the double absolute value bars. I'm just going to write it as u and v without the vector symbols. So magnitude of u times magnitude of v times cosine of the angle between them over magnitude of v times itself times cosine of, and what's the angle between a vector and itself?
0.
So we'd have cosine of 0 degrees. Cosine of 0 degrees is just 1. And then we'd have u times v times cosine of some angle divided by v squared. In this case, magnitude is a scalar, so these do cancel out. And we're left with u times cosine of the angle between them divided by v. If we multiply that by v itself, because remember, we're taking that fraction times vector v, we could rearrange this a little bit, move the divided by magnitude of v over to under the vector itself. And what do you get if you take a vector divided by its own magnitude?
The direction or length.
Yeah, you're left with pretty much just the direction, because a vector is magnitude and direction. If you divide out the magnitude, the new magnitude is exactly 1. You've got a unit vector, which can be thought of as just the direction without any information about magnitude other than the magnitude is 1. This gives us a vector, a unit vector in the direction of v multiplied by a modifier that makes it into the projection. This is ultimately the geometric reason why the projection formula works. This formula turns into a unit vector in the direction of v multiplied by a new magnitude that makes it the correct size for the shadow of u on the v direction. So as dot products, strictly speaking, they don't cancel out. But if you write the dot product as uv cosine theta in that format, you can cancel out the magnitudes and you're left with a geometric version of the formula that really shows why this works at all. Any other questions on that so far?
That was good. Thanks.
All right, let's try filling in the numbers and running the calculations here. The projection of U3 onto V1, we'll use this dot product formula here. So taking those dot products individually, we've got U3.V1. So U3 0111 dot V1 1110. If we take that dot product, what do we get? Yeah, that should be 2, 0 times 1, plus 1 times 1, plus 1 times 1, plus 1 times 0. So 2. And then v1 dot v1 we already calculated for the previous projection anyway. That should still be 3. So 2/3 times v1, which was 1110. So we're subtracting, I think, really the same thing, 2/3, 2/3, 2/3, 0. And then for the other one, we're taking u3 dot v2 over v2 dot itself times v2. And keep in mind, we're using v2 here, the one we just calculated, not u2. So v2 is the -2, 1, 1, 0. And then we'll need these dot products, u3 dot v2. So we take u3, 0, 1, 1, 1, dot v2. What is that dot product going to be? Yeah, that it also happens to be 2. And then v2 dot itself. What do you get if you take the dot product of v2 and itself?
6.
6.
Yeah. 2 squared plus 1 squared plus 1 squared plus 0 squared, 6. So that becomes 1/3 times this vector. And by the way, if we hadn't multiplied the v2 by 3 to cancel out the thirds, we'd be getting a different coefficient here, but this overall result would still be the same. We'd still be subtracting the same projection overall. This projection only cares about the direction of the original vector. So let's see what we get there. We've got 0, 1, 1, 1. We're subtracting 2/3 times 1, 1, 1, 0. So minus 2/3, minus 2/3, minus 2/3, minus 0. And then 2/6 is the same as 1/3. So we're subtracting 1/3 times -2. That becomes plus 2/3. Minus 1/3 times 1. Minus 1/3 times 1. Minus 1/3 times 0. So that's the -2/3 and positive 2/3 cancel out. 1 minus 2/3 minus 1/3 is 0. 1 minus 2/3 minus 1/3 is also 0. 1 minus 0 minus 0 is 1. So v3 is just going to be 0, 0, 0, 1. So it looks like we now have v1, v2, and v3. Those three vectors together should still span the same W subspace as before. There's still a basis for W, but they should now be three vectors that are orthogonal to each other. Any questions on that so far? And let me go back to the geometry of this for a moment. If we think of this as like W is spanned, the original U vectors are just three vectors that create the three-dimensional subspace, but they're not perpendicular to each other. Ultimately, what we're doing is we're taking vector U1, keeping it the same, taking U2 and modifying it so that it's perpendicular, and taking vector U3 and modifying it so that it's perpendicular to all the other ones. So one step at a time, we're making a set of three perpendicular vectors, but modifying just one at a time. Any other questions on those calculations or what they mean? And at the end of this, what's one more thing you could do to check the results, to check the answer?
You multiply them and the dot product would be equal to 0.
Yeah, take the dot products, they should all be 0. All of the mismatched dot products. Like you wouldn't take like v1 dot itself, but v1 dot anything else should be 0. For example, if we take the dot product of 1110.0001, that's definitely going to be 0. You got 1 times 0 plus 1 times 0 plus 1 times 0 plus 0 times 1. Or for instance, v1 dot v2, 1 times -2 plus 1 times 1 plus 1 times 1 plus 0 times 0. That's -2 plus 1 plus 1, so that's also 0. These are orthogonal. Or v2 dot v3, that's also just a bunch of zeros. 0 plus 0 plus 0 plus 0. So these are definitely all orthogonal to each other. And this isn't the only result, by the way. If we had started with U3 and then modified U2 and then modified U1, we'd get a different result, but it would still be an orthogonal basis of W. Any single vector space has infinitely many different bases. We just need a basis that works. Any other questions on that? And also the question here was just asking to orthogonalize, that is to make the vectors orthogonal to each other. If we wanted to take this a step further and normalize to make an orthonormal set of vectors, what does normalizing mean? What would we be wanting to do to the v vectors?
Divided by their magnitude.
Yeah, if you divide each of these v vectors by its own magnitude, what's its new magnitude going to be?
1.
Yeah, we'd be changing them all to length 1. We'd be making them all unit vectors. So for instance, v1, what's the magnitude of v1 here?
Root 3.
3.
Right. 1 squared plus 1 squared plus 1 squared is 3. Well, plus 0 squared is 3. And then we take the square root of the dot product to get the magnitude. So we know magnitude of v1 is square root of 3. So if we take v1 and divide by its own magnitude, we get a new vector that's in the same direction. That's really the important part. Still the same direction, but length 1. So 1 over root 3, 1 over root 3, 1 over root 3, 0. Or we could also just write it as 1, 1, 1, 0 times 1 over root 3. Leave the 1 over root 3 on the outside. And we typically call this vector Q1 in the notation used in the textbook. Q1 is the first part of the orthonormal basis, or one orthonormal basis anyway. So then you'd also take vector 2, v2, divide by its own magnitude, call that Q2. Vector 3 in this case is already unit length, so we can just leave it as it is and call it Q3. So Q1, Q2, Q3 would be an orthonormal basis for subspace W. Any other questions on that? Or orthonormalization in general? All right, what else would you like to work on? Any other topics you'd like to review, or any other questions from that practice midterm, practice final you want to try out?
I was hoping to go over some stuff about, I think we went over it for homework. Let me look it up really quick.
Okay, for what sort of topic?
It's like, suppose V is in the subspace of Rn, and suppose V1, V2, V3 is a basis of V. Decide if the following sets of vectors are a basis for V.
Okay. Well, in order to count as a basis, what has to be true about the 3 vectors, or however many vectors?
It has to have the same dimension as the amount of vectors.
Right, and that's not strictly speaking part of the definition, but it is definitely something that must be true to count as a basis. So if you're dealing with a 3-dimensional subspace, every basis for it has to be exactly 3 vectors. You can't have a 3-dimensional subspace where one of the bases is 2 vectors or 4 vectors. Every basis for a subspace has to be the same number of vectors. That's what dimension means for a subspace. So that is one thing to check. If the set of vectors has the wrong number of vectors in it, then it's definitely not a basis. But even if it does have the right number of vectors, what else has to be true in order to truly count as a basis?
They have to be linearly independent.
Yeah, so that should be enough. If it has the right number of vectors and those vectors are linearly independent, then that should count as a basis. For instance, W we described as the span of these 3 vectors, but we really could have taken any 3 vectors in W as long as they're linearly independent. And typically you could build those using the basis we already have. Like we could have maybe 3 times the first vector, and we could have like the second vector minus the third vector, and we could have the third vector plus 5 times the first vector. Those would be 3 different other vectors in W, but as long as they're linearly independent, they should also act as a basis for W. So I think that's really all you need to check is, does it have the right number of vectors matching the dimension of the subspace? And are those vectors linearly independent? For instance, if you've got a 3-dimensional plane or 3-dimensional subspace, and you have any 3 independent vectors in that subspace, those three vectors that are independent will count as a basis for that subspace. Any other questions on that? Or any other topics?
I'll take a look at the practice one and see if I want to go over anything.
Yeah. Yeah, take a look at that. If there's anything else on that you'd like to work on.
Well, like for me on the test, I tend to struggle with like the true false questions. So
Okay.
I don't know like how I could, I guess like maybe we can go over some concepts.
Yeah. Do you have any particular examples you'd like to try out?
I can look on the textbook really quick.
Sure. It's kind of difficult to generalize about true false questions because there's just so many things that could be asked. But I think one thing to check is if you think something doesn't really quite seem to make sense in terms of this doesn't really seem like it should be true. If it's a universal claim, like if it's saying something is true for everything in a certain category, a good start would be to try to find a counterexample. If you think that this is not really true for everything in the category, one counterexample will disprove it. So that is a good thing to look for. If you're looking for a universal claim, a single counterexample will disprove it. Or alternatively, if it's an existential claim, if the statement is just saying there is at least one example of this thing, or there exists something that has this property, in that case, if it's just saying something exists, all you need is a single example to show that something exists. So those are some useful things to look for. Is it asking, is it claiming that something exists, or is it claiming that everything in a certain category has a property? So that at least will help narrow down what you're looking for, I think. Any other examples you'd like to try out, or any true false questions you'd like to investigate?
I found some on the textbook.
Okay,
Copy and paste them into chat.
sure. Okay, so if m equals n, that is the height and width of the matrix are the same, then the row space equals the column space. So if m equals n, what does that mean about the matrix? What would a matrix look like if the height and width are the same?
A square matrix.
Right, so if you have a square matrix, does that mean that the row space and column space have to be the same as each other?
I want to say no, but I don't know why.
Yeah, it doesn't really seem like they should be, because the row space, what does the row space mean and what does the column space mean? Like for simplicity, let's say we just got a 2x2 matrix. If we just got 4 values here, what would the row space of this matrix mean? And what would the column space of this matrix mean? What are those talking about?
The rows present in the matrix?
Yeah, well, not only the rows, but also how could you combine those rows to get more vectors in the row space? Like the row space is the set of the rows of the matrix and also what else? What can you always do with vectors in a subspace to build more vectors in that same subspace?
We can multiply it by scalar.
Yeah, we can multiply them by scalars, and also how else can you combine different rows?
Row operations.
Yeah, or more generally, I would just say you could find linear combinations of them. You can multiply each one by a scalar, you can add them together, not just for rows, but for any vector space. And this goes back to the closure properties, that if you've got two vectors that are in a vector space, any linear combination of them is also in the vector space. So the row space is not only the rows, but also all linear combinations of the rows. And likewise, the column space is not only the columns, but also all the linear combinations of the columns. But do the set of linear combinations of rows have to be the same results as the linear combinations of the columns? Doesn't seem like they should be, right? Can you give me a counterexample? Can you give me a 2x2 matrix where the rows and columns are not the same information?
One in the row.
1, 1, and then
Say like 8 and 5, I guess.
okay.
Yeah.
In that case, actually, in that case, the row space would be the span of, if we take the rows, usually we write these as columns just for convenience. 1, 1, and 8, 5. But if we've got the span of two linearly independent vectors, what's that span going to be? How much of R2 are we talking about?
And
What would you say is the dimension of this row space?
2.
Yeah, this is two-dimensional because we've got two independent vectors in the basis. And that means if you're talking about a two-dimensional subspace of R2, what's the dimension of the R2 universe?
2.
Yeah, R2 is itself a two-dimensional universe. So any two-dimensional subspace is just the whole universe. So the row space of this matrix is all of R2. And then the column space would be the span of the columns, 1, 8, and 1, 5. Are those linearly independent?
Yeah, yes.
So that means the column space is also a two-dimensional subspace of R2 and is therefore all of R2. So this matrix does not actually work as a counterexample in this case. It is an m by n, a square matrix, 2 by 2, so m equals n. But in this case, the row space and the column space are both all of R2. So in this case, the row space is equal to the column space. But I don't think that's true in general. Can you think of a 2 by 2 matrix where the row space and the column space are not both all of R2? Like maybe where the row space is just one-dimensional, for instance, instead of two-dimensional.
What if we do 1, 2, 3, 6?
Let's try that. 1, 2, 3, 6. And what's special about that matrix that makes you think that's going to work?
It's linearly dependent.
Yeah, these rows are linearly dependent. 3, 6 is just in this case, 3 times 1, 2. So that means in this case, the row space is the span of the rows 1, 2, and 3, 6. But since 3, 6 is just a scalar multiple of 1, 2, that's redundant. It just provides a duplicate of the information we already have. So we don't actually need 3, 6, which means what's the actual dimension of the row space here?
one dimension because
Right. If we only have one vector in the basis, we'd get rid of the other one because it's not linearly independent. One vector in the basis means this is a one-dimensional row space. And the column space should also be one-dimensional. Generally, the row space and column space have to have the same dimension because both of them have dimension equal to the rank of the matrix, the number of pivots. And what's the column space here? That's the span of what?
1, 3.
Yeah, 1, 3. And 2, 6 we'd ignore because that's just another copy of it in a different multiplier. That's also therefore a one-dimensional subspace of R2. So we have two one-dimensional subspaces of R2. They certainly look different because 1, 2 and 1, 3 are not in the same direction. In this case, since it's only two-dimensional universe, R2, we could even graph that out and see visually why they're different subspaces. The row space is the span of 1, 2. So if we take 1, 2, that's this vector, and then the span of that is going to be all multiples of that vector. Scalar multiples of that vector will just make it longer in the same direction, or the exact opposite direction if we use a negative scalar. So this entire line is the row space of A. Whereas for the column space, we take the vector 1, 3. 1, 3. So this vector, and then any scalar multiple of it. A positive scalar multiple will make it longer or shorter in the same direction. Negative scalar multiplier just takes the exact opposite direction. So this infinite straight line is the column space of A. Are those the same vector space?
No.
Yeah, we can tell visually from this graph, these are definitely different. We can also tell algebraically from the fact that 1, 3 is not a scalar multiple of 1, 2. They're linearly independent. But from the graph, it's pretty clear that the only thing they even have in common is the origin, which is a member of every vector space anyway. So these are definitely two different vector spaces, two different subspaces of R2. So I think this works as a counterexample. We've just found a matrix with the height and width equal to each other, but the row space of the matrix is not the same as the column space of the matrix. They do have the same dimension. They're both one-dimensional in this case, but they are not the same one-dimensional subspace, as we can see from the different lines on this graph.
I have a question.
Mhm.
In general, are the row space and column space the same dimension?
Yes, because the way you would find those, how do you typically find a basis for the row space and a basis for the column space? If it's a more complicated matrix than this one.
The RREF.
Yeah, you take it to reduced row echelon format. And then for the row space, you just use whatever rows are non-zero, whatever remaining rows there still are. For the column space, you take, how would you decide which columns to use?
The non-zero, the ones which have a pivot.
Yeah, any columns that have a pivot in the final row reduced form. Of course, you can't take the columns from the row reduced form, but going back to the original matrix, you take the columns in the original matrix that have pivots in the final row reduced form. But in both cases, the number of vectors you get is equal to the number of pivots. The row space, everything in the basis to the row space is rows that have a pivot. The basis for the column space is the columns that have a pivot. So in both cases, the dimension of the row space and the column space equals the number of pivots in row reduced echelon form. And we typically call that the rank of the matrix. The rank of the matrix is the dimension of the row space of the matrix and also the dimension of the column space of the matrix. Because those are both the same as each other. They both equal the number of pivots in the final row reduced echelon form. So for instance, since this matrix only has a one-dimensional row space and a one-dimensional column space, and if you row reduce it, you'd have only one pivot because one of the rows cancels out, we would say the rank of this matrix is 1. On the other hand, if you row reduce it and find that it has a pivot in every column, we would say that is a full rank matrix. Its rank is equal to its number of columns. Or to put it another way, there's a pivot in every column. So a full rank matrix means there's a pivot in every column. Excuse me. Any other
Isn't,
questions on that?
Isn't a full rank matrix like an identity matrix?
When you well, if it's square and you row reduce it, it will become the identity matrix. Yeah. But of course, it didn't have to start out as the identity matrix.
Yeah.
It just has to be row reducible to the identity matrix, which also would mean that it's invertible, and also means the determinant is non-zero, and tells you a whole bunch of other stuff as well. In fact, I think that that idea of invertibility also often shows up on true-false questions. The idea of if a matrix is invertible, what else do you know? Or if it's not invertible, what else do you know? So I think that's also a good thing to keep in mind. Have I shown you the list of properties of invertible matrices?
No, can you share that? Yeah.
I'll post a link to it in the chat. math.anshes.org/m22a/non-singular.html. That's a list of lots of properties that are shared by every invertible matrix. And this really only applies to square matrices, of course. But in general, let me actually pull this up on share screen for a moment. If any one of these things is true for a square matrix, they're all true. Or if any one of them is false for a square matrix, then they're all false for that matrix. For example, let's say you find that a matrix is invertible. Let's say you know it has an inverse. That means that the matrix is non-singular in terms of just the name of the category. And that means everything else on this list is true. Or let's say you find the rank of the matrix and you find that the rank is not the full size of the matrix. That you find, let's say you've got a 2x2 matrix and its rank is 1. That means this statement is false, which means all of these statements are false. All of these statements are equivalent to each other. So for any square matrix, either all of these statements are true for that matrix, or all of these statements are false for that matrix. So this is a very useful way of quickly getting lots of information about a matrix by checking one thing, whether it's true or false, and then you immediately get lots of other information about the matrix. And this is not an exhaustive list. There are, of course, other properties of singular or non-singular matrices that aren't on this list, but are also relevant. So this is just a partial list anyway. But I think it's a good starting point. And of course, you wouldn't necessarily need to memorize all of these, but I would recommend reading through this and making sure that at least the ones that apply to this particular class, like topics you've actually seen in class, make sure you understand why all these are true or all these are false. Any questions on that so far?
Oh, can I actually have a quick recap of dimension again, like just a quick definition of what it means?
Yeah, it kind of means, it's kind of used to mean different things for different situations. If you're talking about a subspace, dimension means the number of vectors in the basis. So for instance, we would say this column space is one-dimensional because its basis has only one vector in it. Or if you take a look at that subspace W we were working with the projections earlier, that was a three-dimensional subspace because it had three vectors in its basis. And in fact, any vector, any basis for subspace W would also have three vectors in it. So it's three-dimensional. If we're talking about a matrix, we usually say its dimensions are usually meaning its height and its width. So we would say the dimensions of this matrix are 2 by 2. So it's mildly annoying that we use the same terminology for the height and width of a matrix versus the number of vectors in a basis for a subspace. So that they're just both called dimension, but they do mean different things.
Yeah.
They're somewhat related. Like this is a 2 by 2 matrix. The dimensions of the matrix are 2 by 2. That tells you that its row space and its column space can't have dimension more than 2. So the row space and column space are at most two-dimensional in this case. But I think that's really the only major relation between those.
Thank you.
Mm-hmm. And if we take reduced echelon format of A transpose, then the pivot columns as column space of A transpose. Yeah. So one way of finding the row space would be to Yeah, is that what you're saying? If you're taking like the column space of A transpose versus the row space of A? So if you've got some matrix A and you're looking for the row space of A, that's just the set of all possible linear combinations of rows of A. But if you take A transpose, the rows of A become what in the A transpose?
The columns?
Right. The rows of A are the same as the columns of A transpose. So row space of A means all possible linear combinations of the rows of A. Column space of A transpose means all possible linear combinations of the columns of A transpose. But the columns of A transpose are the rows of A. So these are the same subspace, just two different ways to write it. Likewise, the column space of A and the row space of A transpose, these are also the same because the rows of A transpose are the columns of A. So the linear combinations of A transpose as rows are the same as the linear combinations of A's columns because the rows of A transpose are the columns of A. They're the same vectors, just turned sideways. So these are really just two different ways of writing the same thing. And you can find them in either way. Like for instance, for row space of A, we usually row reduce A and then take whatever rows remain at the end. For column space of A, we usually row reduce and then take the pivot columns of the original matrix. But you could also find the column space of A by transposing it, row reducing it, and taking the final rows, because those final rows represent the columns of A, or at least linear combinations of the columns of A. But it's usually easiest if you're trying to find the row space and the column space, ideally you only want to have to row reduce the matrix once. And if you row reduce once, all the remaining rows are a basis for the row space. And all the columns with pivots go back to those columns from the original matrix, and that's a basis for the column space. So the advantage there is that one single row reduction operation can tell you both of those subspaces and the null space as well by setting up the results as equations. Any other questions on that? Or anything else you'd like to work on?
Can we do the rest of the true false questions?
Yeah, let me pull back those up to the top. The second one is the matrices A and A and negative A share the same four subspaces. So if we've got matrix A and matrix negative A, and the four subspaces here would be the row space, the column space, the null space, and the left null space, or null space of A transpose. If we take those one at a time, like let's say the row space of A compared to the row space of negative A. Row space just means all linear combinations of the rows. But what about the rows of negative A? If you've just got some matrix, like let's say A, B, C, D, so the row space would be all linear combinations of A, B, and C, D. Negative that matrix would just be negative A, negative B, negative C, negative D. What does that negative multiplier do to the rows as vectors?
Changes the direction.
Right. So for instance, if AB is pointing in this direction, negative A, negative B is pointing in this direction. Does that change the subspace overall?
No. No.
It shouldn't, right? Because the subspace, a subspace isn't just this row, it's this row and all multiples of this row, all linear combinations of these rows, including negative multipliers. So it doesn't really matter if we take this vector or this row versus negative this row. They're still both the same subspace because the subspace includes all the negatives anyway. In fact, even if we had taken like the row space of A versus the row space of 100 times A, any scalar multiplier doesn't change the row space. We'd just be stretching out the basis vectors, but they'd still be a basis for the same space. And I think we should expect the same thing with column space. For instance, if we take the column AC and the column negative A, negative C, those are pointing in opposite directions, but they're still going to span the same space. What about null space? What does the null space of a matrix mean?
Is it the when you multiply it with space, it gives you 0. So like the vectors present in null space give you a 0.
All the vectors that when multiplied by A become 0. So null space of A is all solutions to A times V equals 0, whereas null space of negative A would mean the set of all solutions to negative A times V equals 0. Is this going to have different solutions than this?
Yes.
So what would be different about these solutions?
I'm just saying, assuming if it's a negative sign, so there might be something which in the null space of A, which would sort of not be to 0 over here, since it's a negative sign, they could possibly lead to 0, but I don't know if it's a strong argument.
Is there any way you could modify this equation to make it look like this equation?
Well, multiply both sides by -1.
Yeah, if we just multiply both sides by -1, what do we get?
A times V. No, basically.
Yeah.
0.
So that means it's the exact same equation. Having this negative multiplier here doesn't change the fact that it's the same vector multiplying to 0. If you've got some vector that becomes 0 when multiplied by A, then that vector times A will still be 0 times -1 is also still 0. So it looks like a negative multiplier doesn't change what the null space is. In fact, again, I think any scalar multiplier will have this effect. Like if we had a times 1,000 here, the null space of 1,000 times A is still going to be the same as the null space of A. The times 1,000 doesn't change whether the result is 0 or not, because 0 times 1,000 is still 0, and something that's not 0 times 1,000 is still not 0. And then I think the same argument applies to the left null space also, because the left null space is just the null space of A transpose. And then the null space of negative A transpose is going to be identical by the same argument. The extra negative multiplier doesn't change whether it adds up to, whether it multiplies to 0 or not. Any other questions on that so far? And then part C, if A and B share the same 4 subspaces, then A is a multiple of B. In other words, we're assuming all 4 subspaces are the same for these 2 matrices. So we're assuming we have 2 matrices, and all we know about them is their row spaces are the same, and their column spaces are the same, and their null spaces are the same, and their left null spaces are the same. Does that tell you? I would assume they don't necessarily have to be the same matrix A and B, because we already saw that if 2 matrices are exact opposites with a negative sign multiplier, or even with any scalar multiplier, then they have the same values for the 4 subspaces. So I think we can say if A is a scalar multiple of B, then their 4 subspaces are the same. This one's asking in the other direction. If the 4 subspaces are the same, can we conclude that A and B are, one of them is a multiple of the other? I assume that means a scalar multiple.
If they say it's a scalar multiple, then yeah, but if it's just multiple, like, I don't know.
I think that would include scalar multiples. I'm guessing that when it says A is a multiple of B, I'm guessing that it means a scalar multiple. Because if we're allowed to have matrix multipliers, then that opens up way too many possibilities. So I'm guessing it means A is a scalar multiple of B.
Yeah.
Yeah, I think that seems reasonable, because if the row spaces are the same, that at least means that all the rows of A are linear combinations of the rows of B.
Exactly.
Which could include maybe they're scalar multiples of each other, which is what we're trying to check. If that's the only difference, that they're scalar multiples of each other, then we're done. They might also be rearranged, which means the matrices are not just multiples of each other. But if the rows are rearranged, what would that do to the columns? If you rearrange the rows, does that change the columns?
Yeah.
Yeah. Row operations such as swapping rows or adding a row to another row, those keep the row space because it's just linear combinations of the rows, but that would scramble up the column space. So I think we can say this is not just a case where A and B are row equivalent to each other. It's more specific than that. A and B cannot have the rows rearranged and cannot have a row added to another row, because that would scramble up the column space, which means the column spaces would not be the same. So I think the only thing that could be done between changing A to turn it into B would be maybe multiplying some rows by scalars. In fact, I think they'd all have to be multiplied by the same scalar, because like if you multiply the top row by 3 and then multiply the second row by 4, you're not preserving the column space. The columns would be changed to a different direction. So I think the only difference between A and B, if we want the row spaces to be the same and we want the column spaces to be the same, they have to be not necessarily the same matrix, but at least the same matrix up to an extra scalar multiplier. Maybe A is negative B, or maybe A is 3 times B, or something like that. And of course, it doesn't even have to be a whole number. It could be like A equals 3.7 times B, for instance. But it's got to be some scalar multiplier times B. Any other questions on that? Or any other questions before I go?
Just to clarify, so the answer for C would be true, right?
I think that is true, yeah. The only way that they can have the same 4 subspaces, like their row spaces are the same and their column spaces are the same, the null spaces are the same. I think the only way that can happen is if they are maybe the same matrix, or maybe one of them is a scalar multiple of the other. But they can't be any more different than that.
That makes sense, yeah.
Any other last questions?
You don't have to do the whole sum, just but like in the you had submitted like a practice final, right?
Mhm.
In that, the question 10, is that asking us to find the projection matrix, which will be
It's kind of related. T in that one is not actually a projection matrix, but it is a function in the sense that it takes a vector as input and gives you another vector as output. I don't think this topic was actually covered in this class. Sometimes they cover it, sometimes not. But the idea is any function that takes a vector as input and gives you another vector as output, as long as it follows certain rules, specifically distributing over linear combinations, then that function can be represented as a matrix multiplier. So a projection matrix is one example of that sort of transformation matrix. But there are many other examples as well. And the problem 10 problem 10 in that practice final is, it doesn't tell you what the matrix is, but it tells you if the input is 2, 3, then the output is 1, 1, 1. And if the output is 3, 0, then the output is 0, 9, 3. And I think that is enough information to write out matrix T using row reduction, but I don't think that was actually covered in this class.
okay, that's cool. So that just to clarify, also T would be a 3x2 matrix, right?
Yes, because it needs to turn a 2x1 vector into a 3x1 vector.
Okay, cool.
Yeah. All right, then I'm going to take off. Feel free to let me know on Discord or by email if you have any other questions. Good luck on finals and have a nice break. And I hope
Thank
to
you
see
so
you
much.
in 22B sometimes. You're welcome.